morning. Thanks for coming. My name is Jeremy Jernigan, and it's my pleasure this morning to introduce the lecture today by Steve Loucks. If everyone could remember to mute your phone, that would be good. And just very briefly, many of you know Steve, but he received his MFA from Alfred University in 1985 and taught at Jacksonville State University for 27 years, retiring just 2 years ago to focus entirely on his practice as a studio potter in Wellington, Alabama. And Steve has been a great source of information and expertise, especially in the realm of pots and glazes for many years. And he's been featured at a number of past NCECA conferences as a panelist and a topic leader, with topics including switching to cone 6 glazes, cone 6 without compromise, cone 6 without shame. That last one was just mine. He's also served as one of our NCECA glaze doctors. So this morning, his lecture is entitled An Easy Way to Adjust Glazes. Please welcome Steve Loucks.
Okay, so glad everybody's here today. I just want to do this little formality here. Okay. I feel very fortunate to have met Ted Randall, an intelligent man, inquisitive, very well organized and systematic, soft-spoken, and one of NCECA's founding fathers. Ted Randall, along with a few others, realized their vision to have an annual conference where ceramic artists and educators would come together and share their knowledge and ideas and experiences. I am very pleased to be a part of that vision here today at NCECA, sharing some of my knowledge, ideas, and experiences by presenting this lecture as an easy way to adjust glazes or glazes that need some tweaking. My glaze testing method is a simple kitchen method approach that is from a potter's perspective for testing, developing, and adjusting glazes that I feel is effective and very useful. I like this method because I am a visual artist, and this method goes right to the glaze test that visually reveals how a particular ingredient directly influences the glaze, as opposed to a chemical engineering approach that requires initial calculations with lots of math, using molecular, empirical, and limit formulas. And very importantly, it reveals how much and to what extent that particular ingredient affects the glaze to produce that particular effect. So how fast is fast? How hot is hot? How glossy is glossy? How opaque is opaque? Or how much does that glaze bead up? As in this example, where magnesium carbonate, this test shows how the influence of magnesium carbonate when added in increasing amounts to a simple base glaze. I can then choose which stripe produces that particular quality that I like with the correlating amount of the influence ingredient, which is written on the back of the test tile, and then make up that glaze. In this example, I used a very simple base glaze, just nepheline cyanide, 100% with 2% copper carbonate. That base glaze is the far left stripe. Then I added 10% increments of an influencing ingredient to see how it affects that base glaze. I like the middle stripe, so I chose that stripe with that recipe to mix up and then glaze this bottle. This is just for fun. The influence ingredient in this piece is Comet Cleanser in this glaze. So it's just 100 grams of nepheline cyanide plus 2 grams of copper carbonate and 20 grams of Comet Cleanser. I believe Comet Cleanser contains borax, which has boron and sodium, which are low melting flux materials. It's just 100% nepheline cyanide, 2% copper carbonate, and 20% Comet Cleanser. You'll understand as we go on. So who came up with all those limit formulas anyway? And for what kind of ceramic endeavors? Artists? No. Artists like to break the rules and push the limits. For example, macrocrystalline glazes have exceedingly high amounts of zinc in their glazes. Fake ash glazes have exceedingly high amounts of calcium in them. They don't fit into those limit formulas designed by the engineers. And every Shino glaze I know of, which is very high in sodium, crazes. This is a close-up detail of my Shino glaze. I don't necessarily prefer glazes that craze, but I love Shino glazes. So that's okay with me. It's a crackle glaze. Crazing is when the cracks in the glaze are undesirable, and a crackle glaze is when they are desirable. Okay, before I explain my testing procedure, I need to express how the application of the glaze is a very important influencing factor affecting the outcome of the glaze, along with the firing. For many glazes, to achieve that particular desired effect or look, the application of the glaze is the definitive factor for success. For example, I enjoy layering glazes and sometimes multiple firings, as in this piece. How the glaze is applied, as in this image, dipped, poured, brushed, or sprayed, is very important. Each of these methods applies the glaze having slightly different thicknesses, which can dramatically affect the outcome of the glaze. Even how thick or thin the glaze was originally mixed up, or what temperature the piece was misfired to, or how thick or thin was the clay body wall, and even how long you hold the piece down in the bucket of glaze affects the absorption of the glaze and therefore the outcome of the glaze. I use this glaze all the time. This test tile shows how runny this glaze can be depending on how it is mixed up. With this example, more water was added to the glaze before each consecutive brush stroke, going from very thick to very thin. Note how runny it is when the glaze is made up rather thickly, as shown here in the first stripe on the left, whereas how nice it can be, as shown here on the right, with just the right amount of water, with the third stripe. Glaze recipes never list how much water should be added to the batch of glaze. Experience is the best teacher. Another factor is the color of the clay body. These two bottles are glazed with the same glaze and fired to cone 6 in an electric kiln. The bottle on the left is a white stoneware, whereas the bottle on the right is on a dark brown clay body containing granular manganese dioxide. Another factor is the firing atmosphere. These two bottles have the same glaze. One was fired in an oxidizing electric kiln and the other is fired in reduction. Both were fired to cone 6. Temperature differences throughout the kiln are another factor. Almost all kilns have hotter and cooler areas. These two cups were glazed with the same glazes at the same time and fired in the same kiln. The left one was placed in the bottom and the right one in the top of my kiln. I often place pieces with this particular glaze in that part of the kiln and this glaze in that part of the kiln. Again, experience is the best teacher. These two bottles were glazed with the same glazes at the same time and fired in different kilns to cone 6. The bottle on the left was fired to cone 6 using the slow program, and the bottle on the right was fired to cone 6 using the slow program plus a down firing. I love to use a down firing with all my firings. And then don't dismiss the kill god or goddess who just loves to play with your head, meaning stuff happens. I was going to say, these were fired in a soda kiln, and this happened 1 month before my MFA show at Alfred. It was quite a freak out, actually. We never found out what really caused the glazes to froth or foam, as shown here. I should have exhibited in my show, but I didn't. This is the dinner set with the exact same glaze in the next firing. Same kiln. And this teapot is a collaborative work by Lynette Hesser, my wife, and I, and it has the same glaze but fired in a reduction kiln. I feel that there are no bad glazes. Just look at the popular crater glazes. Yeah. Glazes that are deemed as undesirable are due to just a bad application or firing process, the wrong glaze put on the wrong piece, or it just needs a little tweaking and adjusting. So now, to better understand how to adjust a glaze, let me briefly discuss what is a glaze. In theory, glazes are composed of three essential materials: glass, flux, and clay. Ceramic artists use two main glass formers to make glazes: silica and boron. Silica is by far the most useful, effective, and available glass former. It is one of the main materials in all of our glazes. But silica melts at a very high temperature, around 3110 degrees Fahrenheit, which is a temperature well above what our kilns easily fire to. So we need to lower the melting temperature of the silica down to a desirable temperature range. To accomplish this, we add flux. Flux ingredients are those materials that readily react with silica to lower its melting temperature and make it look like glass, like window pane and bottles. Note that the term glass is used to both refer to silica and also to a mixture of silica and flux, which is what window pane is, and bottle glass. Often, the reactions of the silica and flux mixtures cause them to melt uncontrollably and flow off the pot onto the kiln shelf. Now we need to add clay. Clay can control the melt and flow of the glaze, its viscosity. Clay also raises the melting temperature of the silica and flux mixture. Once clay is added to the glass plus flux mixture, it is now a glaze. That is what glaze is in theory: glass plus flux plus clay. In reality, Mother Nature helps us out with a material called feldspar, which is made up of silica, a glass-forming material, various flux materials that lowers its melting temperature, and clay, which controls its melt and flow, the three essential glaze materials. Feldspar makes a glaze all by itself, but is not totally wonderful. This is nepheline cyanide on the left and custard feldspar on the right, fired to cone 6 in an electric kiln. This is nepheline cyanide with 2% copper carbonate added just to see the results a little bit easier in my tests. Since the feldspar by itself is not totally wonderful, let's say if you're going to use it on utilitarian pottery, for example, it needs to be modified by adding more flux ingredients to improve both the melting of the glaze and give it its particular qualities. Then some clay and silica are added. Special note: the particular flux that you use often gives the glaze its particular characteristics or quality, its look. For example, when the flux scarcity borate is added to nepheline cyanide and copper carbonate, it lowers the melting temperature of the feldspar and produces a fluid, glossy surface with a greenish color response. Whereas, when the flux strontium carbonate is added to nepheline cyanide and copper carbonate, it lowers the melting temperature of the feldspar and produces a matte surface quality with a turquoise color response. Increasing amounts of the flux often lowers the melting temperature of the feldspar, which eventually causes it to flow uncontrollably, as shown here in the far right stripe. So, more clay is added, like the common ingredient EPK, to that mixture in the last stripe to control the flow of the feldspar and flux mixture. So here's the EPK was added to the last stripe in the previous image in 10% increments. This is what a glaze is made up of in reality: feldspar plus flux plus clay. The following bottle is glazed and made up with the third stripe on this test. So that's all it is, just nepheline cyanide, strontium, and clay. Glazes are a balance between the feldspar, which is often the largest component ingredient and the bulk of the glaze, with the various flux ingredients, clay and silica. Feldspar is the foundation of the glaze. The flux, clay, and silica ingredients are added variables that are mixed up in different combinations in relation to both themselves and to the feldspar to create the particular glaze. Glaze recipes should always be listed in this order to better understand and evaluate the glaze. First, feldspar. Second, the flux, highest to lowest amounts. Third, clay. And fourth, silica. That should be summed up to 100%. Then list the colorants, and lastly, the additives. Understanding a glaze recipe helps us to assess the glaze to better understand How to adjust the glaze. Let me divide glazes into two categories, matte and gloss glazes. First, the feldspar content will almost always be the highest amount of any ingredient in the glaze. Therefore, it is the bulk ingredient and the bulk component part of the glaze. Matte glazes generally have a high clay content, whereas glossy glazes have a relatively high silica content. So let's compare some glaze recipes that were taken from a ceramic glaze book and some that I have used. I did not include the colorants, so the following images show two recipes side by side. Which one is the glossy glaze? Which one is the matte glaze? So note that the feldspar is the bulk of the content in both glazes. Secondly, barium, which is the main flux of one of the glazes, promotes a matte surface. Thirdly, the second glaze is much higher in silica. So which one is the matte glaze? Which one is the glaze on the left is matte and the glaze on the right is a glossy glaze. Note that, again, the bulk of the glaze content in both glazes is feldspar. Secondly, one of the glazes has a high silica content where the other glaze has no extra silica in it. The glaze on the left is the glossy glaze, and the one on the right is the matte glaze. Again, the bulk of the glaze content in both glazes is the feldspar. Secondly, one of the glazes contains a strong, low-melting flux Gerstly borate. Thirdly, one glaze has no extra silica in it. Fourth, one of the glazes is very high in silica with a very low clay content. Therefore, you can conclude the glaze on the left is a matte glaze and the glaze on the right is a glossy glaze. You may recognize one of these. The bulk of the glaze content, again, is the feldspar. Secondly, the flux strontium promotes a matte surface, okay? Whereas Gerstly borate in the other glaze is a strong, low-melting, glossy flux. Thirdly, one of the glazes has a very high silica content. The glaze on the left is a glossy glaze, and the glaze on the right is a matte glaze. And lastly, again, the feldspar content in both glazes is the highest and the bulk of the glaze. One of the glazes has a high amount of Gerstly borate, a strong, low-melting flux. And thirdly, one of the glazes is very high in silica. The other glaze has no extra silica. So the glaze on the left is a glossy glaze, and the glaze on the right is a matte glaze. Glaze recipes arranged in this order, summed up to 100%, can reveal patterns, cluing one to guesstimate some of the qualities of the glaze and to help target which ingredient needs to be added to the glaze to adjust it to achieve a particular desired result. Now back to adjusting a glaze. Okay, I started using this glaze testing method of adding increments of an influencing ingredient to a base glaze on an L-shaped tile way back as a graduate student at Alfred, where I was asked to teach the raw materials lab class to the undergraduates. As done many times, if I remember correctly, we began by testing combinations of feldspar with increasing amounts of flux, mixed up dry, packed into a tiny thimble, and then transferred onto a flat tile, retaining the thimble shape. This image shows a fusion button test tile display for the flux ingredients. Back then we tested custard 100%, then custard 90 with whitening 10, and then 80-20, and so on. They were fired to different temperatures. So that's way too much work for me. And more importantly, who would ever apply a glaze like that? So it didn't directly relate to the way we apply our glazes, which is so important. So we did the same test, mixing up the same amounts, except we added some water and brushed them onto the L-shaped tile of my design, as in this example of nepheline cyanide plus copper carbonate, to see the test results easier, with additions of a lithium carbonate, a very strong melting flux. This tile design tests the response of the influencing ingredient on a base, revealing how it behaves to vertical flow, horizontal pooling, over a slip, breaking over texture and pooling in depressions, all on one test tile. The formula and the influence ingredient, along with their amounts, are listed on the back. So this is how the testing method works to adjust a glaze. First, you make a 6-inch tile with slip on the top half if you want to see how the glaze will respond over a slip, with textured lines on the top and the bottom made by dragging a fork through the clay, and then bend the tile into an L shape. After it is bisque fired, label the back of the tile with an underglazed pencil the complete recipe for the base glaze, the influence ingredient to be tested, and in what amounts, the date, and the title of the glaze. That way you don't have to refer to your notebook later on, and 10 years later, it's right there. You don't have to go back. Then mix up the base glaze to be tested. I like to mix up a 200-gram batch for better accuracy using a small blender. Brush on a stripe of the base glaze on the far left side. Next, add a particular amount, for example 10%, of the influence ingredient to be tested into the base glaze, mix thoroughly, and make a stripe of that mixture. Then add another 10%, which now makes it a total of 20% of the influence ingredient to be added to that mixture. Mix thoroughly and brush on a stripe of that mixture. Then add another 10%, which now makes it a total of 30% of the influence ingredient. Mix thoroughly, brush on a stripe of that mixture. And lastly, add another 10%, which now makes it a total of 40% of the influence ingredient added to the base glaze. Mix thoroughly and brush on a stripe of that mixture. Then fire the test tile in one of your normal firings. In this test, EPK was added to produce a matte glaze. So then you assess the fired tile showing how the influence ingredient, which in this case is EPK, affects the base glaze, making the glaze go from a glossy to a matte glaze. Choose which stripe is most desirable. Again, remember how glossy is glossy? So you can see, you can choose which tile you like best, or which stripe you'd like best. So let's choose the third stripe with a 20% addition as the mixture that we'd want to mix up and use. This bottle is glazed with that recipe from that third test stripe. Now you need to convert that glaze recipe to 100%. So you add the 20% addition to the total of all the base glaze ingredients, which in this case totals to 120. Divide each amount in the base glaze and the influencing test ingredient by that total, 120. Round off the numbers to the nearest and whole number. That tenths and 1/100% is insignificant, in my opinion, compared to all the other influencing application and firing factors that I mentioned previously in the beginning of the lecture. This will give you a recipe totaling 100%. Write down the new recipe in the correct order. That's very important. The colorants should remain the same. So I feel this testing method of adding increasing amounts of an influencing ingredient into a base glaze to achieve a particular desired result is very effective way to adjust and develop a new glaze and see all its possibilities. The best way to see that role of that particular ingredient in the glaze is to just take all of it out of the glaze recipe and then add it back in increasing amounts. This way, the true role of that particular ingredient is clearly exhibited. Often, testing just one component part, for example, just taking out the clay ingredient and adding it back in, will adjust the glaze to accomplish a desired result. Many times, that same result can be achieved using different methods. Either way. To lower or raise the melting temperature of a glaze, so I'm going to show some examples of how to lower or raise the melting temperature of a glaze, to control the flow of the glaze, to make the glaze go more glossy or matte, to change the color of glaze, and to adjust an undesirable, already mixed up wet batch of glaze into a working glaze. There are several ways to accomplish these results, and one adjustment can accomplish more than just one goal. For example, to control the flow of a glossy glaze, one can adjust the clay amount, or you can adjust the silica amount. Both will affect the flow of the glaze, but in different ways. The following tests will show results which You can then choose which stripe you like best and then mix up that recipe. Remember though, adjusting one component can change some of the glaze's qualities in an unexpected way. Often that is with the color response. Again, glazes are a balance between the feldspar and the various flux ingredients in relation to the clay and silica contents. Okay, to show how to adjust the glaze, I separated the test into two main groups, matte and glossy glazes. To lower the melting temperature of a glossy glaze that has Custer feldspar in it, the first thing you should do is try substituting nepheline cyanide, which is a lower melting feldspar, for the Custer feldspar. And then you might want to add a strong low melting flux like Gerstli borate. In this test, to lower the melting temperature of the common amber celadon glaze, which is a cone 10 glaze, to cone 6, I first substituted nepheline cyanide for the Custer feldspar, and then I added Gerstli borate in 5% increments. I then chose the middle stripe with the 10% addition of Gerstli borate for that amber celadon glaze. And this is the bottle. And then, since the glaze reveals texture so wonderfully, the way it breaks over an edge and pools and depressions, I used it to glaze one of my teapots over the textured handles. So this is fired to cone 6 in an electric kiln. I also ran a color test on that amber celadon base and developed this red glaze. So this is fired to cone 6 in an electric kiln using that same base glaze. Now there are several ways to lower or raise the melting temperature and control the flow of a glossy glaze. One is to take out all of the flux and add it back in 10% increments. Note how the flux ingredients take the glaze from a very stiff, dry, and eventually to a runny, glossy glaze. I liked between the second and third stripes, so I made up the glaze using a 15% addition of flux ingredients. This is the glaze on a carved pedestal bowl by my wife, Lynette Hesser. So you see how simple it works. Or you can take out the dominant flux in a glaze recipe and then add it back in 5 to 10% increments. Note how runny the glaze gets as more of the dominant flux is added. Or you can take out all the clay and then add it back in 10% increments. Note how increasing amounts of clay affects the flow of the glaze. Or you can take out all of the silica and add it back in 10 to 15% increments. Note how increasing amounts of silica can also control the flow of the glaze as it raises the melting temperature. Now, to lower or raise the melting temperature and control the flow of a matte glaze, take out all the dominant flux and then add it back in 5 to 10% increments. Note how increasing amounts of strontium carbonate lowers the melting temperature of the glaze and eventually causes it to flow uncontrollably. I chose the middle stripe with a 20% addition of strontium carbonate and added it to this glaze, or added to make this glaze for this bottle. Or you can take out all the clay in that same glaze recipe and add it back in 10% increments. Note how increasing amounts of EPK raise the melting temperature. Also note how the second stripe is similar to the third stripe in the previous test to make the matte glaze go from too matte to a softer matte, then satin, and eventually a glossy surface. Take out the silica and then add it back into the glaze in 10 to 20% increments. Note how the glaze changed from a matte glaze to a glossy glaze with these additions of silica, which is the glass former in our glazes. I chose the last stripe, mixed up that recipe, and glazed this bottle. And then I glazed this piece, just to show you how it looks on one of your pieces. Next is another example of where silica was added back into the glaze in increasing amounts. Note how the silica affected the matte surface quality and eventually went glossy. I like the second stripe most with a 10% addition of silica in the glaze recipe. So I mixed up that glaze recipe and glazed this bottle. Now, to lower the melting temperature of a glaze, you may want to just add a frit, like frit 3124, to the glaze in 5 to 10% increments. Frits are industrially made flux ingredients that behave like low melting feldspars. So adding a frit sometimes eliminates the particular surface quality and color influences that are often produced by certain fluxes, like strontium and barium. Or you can add the strong, low melting flux like Gersley borate in the same amounts. Now, to make a glossy glaze go matte, or a matte glaze go glossy, take out the clay and add it back into the glaze in 5 to 10% increments. Note how the additions of EPK, the clay, can produce a matte glaze. Or take out the silica content, so I'm showing several different ways, and add it back into the glaze. I like the soft satin quality created by the second stripe with the 10% addition of silica to the glaze, so I made up that for this bottle. Here is another example of the common Don Wright's glaze, which is a matte glaze, and I added silica to it to make it into a glossy glaze. Note how it changed the color response when you turn it into a glossy glaze. So to sum up this glaze test, this series of glaze tests, I showed how to adjust a glaze by taking out all of the flux ingredients in the recipe and then adding them in, or the clay component and adding it back in, or the silica component and adding it back in 5 to 10% increments. So now what do you do with all that glaze waste? Okay, be as environmentally responsible as you can. Don't throw it out. So collect and save all your glaze testing materials and put it in a container labeled a slop glaze. And then when you have enough of that waste or glaze accumulated, mix it up to a normal glaze consistency and test it. Assess and determine what it needs to be adjusted to make it into a working glaze. For example, this slop glaze, as you can see on the far left side, was too matte. So I wanted a glossy glaze. So I adjusted it to make it into a glossy glaze by adding 10% increments of dry silica to 500 grams of a wet batch of slop glaze. I know it can't be reproduced, but enjoy it while you can, and it's better than just throwing it out into the environment. Okay. I love to spray my glazes. So to collect and reclaim all the overspray, I built this spray booth with a large squirrel cage blower in the back to draw the air out the back, and then a PVC pipe in the upper back with holes in it that creates a stream of water flowing down the metal back plate to catch the overspray and wash all the glaze materials down into a bucket of water below with a simple pump to regenerate recirculate the water. I periodically clean out that bucket and save all the glaze waste. When I have a sufficient amount of glaze waste, I mix it up to a typical glaze consistency and test it on a broken shard and then observe it. After observing one glaze shard I noticed of a slop glaze, I guesstimated that it needed EPK and added it in to control the flow of the glaze. So what I did was I took 500 grams of the wet batch of glaze, weighed that out, and then I added 50 grams of dry EPK to that. So the first stripe is just the wet batch of glaze, then 50 grams, which is 10% since it was a 500 gram batch, then another 10%, another 10%, another 10%. Then I fired the tile. I looked at it. After observing the fired test tile, I chose which stripe that I liked best. I chose the second stripe in this example with a 10% addition of EPK, which was then added to the 500 grams of the wet slop glaze. So then you have to figure out what to do with the rest of the glaze. So I weighed out the rest of the slop glaze. Let's just say that it weighed out to 10,000 grams. Then I divided the weight of the 500 grams, so 10,000 by divided by 500, which is the weight of the test batch, equals 20. So I multiplied the 50 grams that I needed to add to make it a workable glaze by that number. So 50 times 20 equals 1,000 grams. So I weighed out 1,000 grams of EPK and added it to the 10,000 grams of the slop glaze. I added a little bit more water as necessary. This glaze should now relate and match the second stripe of the test tile. And so this is the bottle of the newly adjusted glaze. I had another one to change the color of an already mixed up wet batch of glaze. I added 1 to 5% increments of metallic oxides, or you can use commercial stains and do the same testing procedure. I wanted a black glaze, so I tested a 500 gram batch of slop glaze, which is exhibited here on the far right left stripe, and then I added increments of cobalt carbonate. I like the second stripe, so I made up that batch of glaze just as I explained before. And here's the bottle of that slop glaze. So then to conclude, these are just some of the ways to adjust a glaze. Just a second, I think So then I took that black glaze right there and the previously adjusted brown glaze, and I used it on one of my pieces. So don't throw out that slop glaze. Adjust it to, and then you can use it on one of your pieces. So to conclude, these are just some of the main ways to adjust a glaze, but by no means the only ways. I think you will find this method of glaze testing using the L-shaped tile and adding increments of an influence ingredient to a base glaze to be the easiest, most resourceful, direct, effective, and useful glaze testing method. Remember two things. One, glazes are very finicky and love to tease, mislead, and confuse you. But some wonderful glazes can be achieved. Also, the bottom line is that you have to test the glazes with your application in your studio and fire them in your kiln the way you like to fire the kiln. Okay. Thank you so much. Feel free to contact me if you have any questions. And enjoy your life.